Hello guys, welcome back to my YouTube channel again. So in this video, I am actually going to evaluate an integral using the First Barnes Lemma that I actually stated and proved 2 videos ago. And this integral is quite famous because it's by Ramanujan. So the integral in question, which I will always call I, equals integral from minus infinity to infinity of the product from k equals 0 to infinity of 1 over 1 plus x over k plus a the whole square times 1 over 1 plus x over k plus b the whole squared dx. And the condition on this integral is that the real part of a and the real part of b are both greater than 0. Before we do anything, let's actually recall the first Barnes lemma. So it states that if we have 1 over 2 pi I times the integral from minus I infinity to I infinity of gamma of alpha 1 minus s, gamma of alpha 2 minus s, gamma of beta 1 plus s, gamma of beta 2 plus s ds, that equals gamma of alpha 1 plus beta 1 times gamma of alpha 1 plus beta 2 plus times gamma of alpha 2 plus beta 1 times gamma of alpha 2 plus beta 2 divided by gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 2. And this is true as long as the real part of alpha I plus beta j is greater than 0 for all ij, and we're placing the integral such that the real part of s, which is the integrating variable, is between minus real part of beta j, it's greater than the minus real part of beta j, and less than the real part of alpha I for all ij. Okay, and in the video where I actually prove this lemma, I said that we can weaken the condition such that we make the condition such that the real part of alpha I plus beta j for all ij is not a negative integer. That's only possible if we're analytically continuing the gamma function into the negative plane. For all our intents and purposes, and this kind of standard choice for this the real part of s, we're assuming the gamma is defined only on real part of z greater than 0. Okay, so with that being clear, let's actually consider the product that was inside the integral. So say we have the product from k equals 1 to infinity, 1 over 1 plus x over a plus k the whole square. That can be actually expressed as taking a common denominator, product from 1 to infinity in k. We have a plus k the whole square in the numerator, which I can write as a plus k times a plus k, divided by a plus k whole squared plus x squared. Now I can factorize the denominator as a plus k plus ix times a plus k minus ix, and set that equal to the product from 1 to infinity in k of 1 plus a over k after dividing the numerator and denominator by k times 1 plus a over k divided by 1 plus a plus ix over k times 1 plus a minus ix over k. Fair enough. Now, to sort of simplify this big ensemble of a product, we're going to use the Weierstrass definition of the gamma function. And again, this is valid as long as the argument inside gamma is non-negative. So it shouldn't be 0 or negative. So it should be positive, the argument inside the gamma. So gamma of z plus 1 equals e to the minus gamma z, product k equals 1 to infinity, e to the z over k divided by 1 plus z over k. So now let's set z equal to k, z equal to a plus ix, and z equal to a minus ix, multiply them such that we're multiplying the gamma of a plus ix plus 1 times gamma of a minus ix plus 1, and then dividing by the a term, which is gamma of 1 plus a times gamma of 1 plus a. And if we just use the Weierstrass definition for the gamma function for this left-hand side, we end up with e to the minus Euler-Mascheroni a plus ix e to the minus Euler-Mascheroni a minus ix divided by e to the minus small gamma a e to the minus small gamma a times the product from k equals 1 to infinity of e to the a plus ix over k e to the a minus ix over k divided by e to the a over k times e to the a over k times product 1 plus a over k times 1 plus a over k divided by 1 plus a plus ix over k times 1 plus a minus ix over k. Well, the left hand side is just the same. I'm not going to repeat that. The right hand side now, actually, you see that all the exponential terms will cancel out nicely. So we just get product from k equals 1 to infinity, 1 plus a over k, 1 plus a over k divided by 1 plus a plus ix over k, 1 plus a minus ix over k. We can simplify the left-hand side using the recurrence relation of the gamma function. So we get a plus ix times gamma of a plus ix times a minus ix times gamma of a minus ix divided by a times gamma of a times gamma of a equals, now the right hand side is actually just the product we considered before the Weierstrass definition, which is this. So we can just substitute that in. It's the product from k equals 1 to infinity of 1 over 1 plus x over a plus k, the whole thing squared. We can simplify this. We can remove all these factors of a's and x's, put them on the right side. So we get gamma of a plus ix times gamma of a minus ix divided by gamma squared of a, which equals, now, simple, just writing all these prefactors on the right side, we get 1 over 1 plus x over a the whole squared times the same product as before. But notice that if k were 0, we would just get the term that's multiplied with the upfront. That means we can just start the product from k equals 0 because this is already multiplied with the rest of the terms. So we have a product from k equals 0 to infinity of 1 over 1 plus x over a plus k the whole squared. And this is exactly what was inside the integral I. Instead of just having one of them, we actually had two of them, one with an a, one with a b. So we can just substitute for each of them because we can split the product into the first product times the second product. So we get integral minus infinity to infinity gamma of a plus ix times gamma of a minus ix divided by gamma squared of a times gamma of b plus ix times gamma of b minus ix divided by gamma squared of b dx. Notice that the real part of a and b are both greater than 0. So there's no real poles because for there to be poles, the gamma function should have an argument of a non-positive integer, which means 0 and all the negative integers. And that's not really happening because, real part of a and the real part of b are greater than 0. So the denominator is definitely not doing that. The numerator, which was, is the more valid point of concern, is also not blowing up because even if x becomes that non-positive integer, a is always going to be greater than 0. So we're not going to have that. And that's why we can actually do this change of variables. X goes to ix and not really change the integral because this is not just a simple substitution like x equals ax where a is some real number. When you multiply by I, you're actually rotating the entire integral by 90 degrees in the complex plane. So you actually need to argue that this segment along the real axis is equal to the segment along the imaginary axis because the closure, the quarter circle closure in this case, will go to 0 because of the asymptotics of the gamma function at infinity. At real part goes as imaginary part goes to infinity. Sorry. I'm gonna skip that closure argument. You just use Stirling's formula and write it out in the special case that the imaginary part dominates, and you should do your analysis and come to the conclusion that, well, since there's no poles, just rotating the contour just keeps the integral invariant. So integral I is now, with this change, x goes to ix, integral from minus I infinity to I infinity, gamma of a plus x, gamma of a minus x, gamma of b plus x, gamma of b minus x divided by gamma squared of a, gamma squared of b, dx over I. Now we can just use the first Barnes lemma for alpha 1 equals beta 1 equals a, and alpha 2 equals beta 2 b equals b. For alpha 1, alpha 2, beta 1, beta 2 are basically how we define them at the start of the video. So we just need to verify the condition for the first Barnes lemma to be applied. We need real part of alpha I plus beta j to be greater than 0 for all ij, summing over 1, 2. Well, in the first case where when we take real part of alpha 1 plus beta 1, we get real part of real part of a plus a, which is just the real part of a because, the 2 doesn't matter. Is that greater than 0? Well, it is because, we chose at the start of the video that the real part of a is greater than 0. Similarly with the b, if we take alpha 2 and beta 2, we get real part of b has to be greater than 0, and that's satisfied. That's true from assumption in the beginning. The other thing that needs to be checked is the real part of a plus b is greater than 0. Well, it is because real part of a plus b is real part of a plus real part of b, and both of them are already greater than 0, so this has to be greater than 0, and that's satisfied. It's just that in our case, the way that we have our integral set up, the real part of x, which is the integrating variable, is 0. And that actually works because since real part of b is greater than 0 minus real part of b is less than 0, which is less than real part of x, which is 0, which is less than real part of a, which is greater than 0. So, even our region of convergence, our window, our standard choice for the analytic gamma function on the positive half plane, it works. And we can just use the first Barnes lemma, just use the right-hand side of the first Barnes lemma to evaluate this integral. And we get I equals 2 pi divided by gamma squared a gamma squared b times gamma of 2a, gamma of a plus b, gamma of a plus b, gamma of 2b divided by gamma of 2a plus 2b. And we can just use the relation between the gamma function and the beta function to rewrite this as 2 pi times beta of 2a comma 2b divided by beta squared of a comma b. And that's it. That's it. It's a very, very nice compact result because this integral had an infinite product and it was an improper integral from minus infinity to infinity, the entire real line. And you basically just get this nice compact form in terms of the beta function, just out of nothing. All thanks to the brilliant first Barnes lemma. So this serves as a very, very good application of that lemma. The second Barnes lemma could also be considered as a corollary of that, but this is just way more notable because this was discovered by Ramanujan. So the literature says. And of course, we can, add more variables, take it to more dimensions, so that, you're integrating over 3-dimensional, 4-dimensional space from minus infinity to infinity. And you would get, like a product of these beta functions for each dimension. So that's it, guys. Thanks for watching. I'm sorry I have been a little lazy with my video uploading. And you may notice that my recording setup isn't what it usually is. It's because I'm in London and I still haven't really moved in yet. So see you in the next video. Peace out.